Welcome to Lecture 1.5. In this lecture, I'll be covering multiplicity, or the shape of the signals of 1H NMR, and the information that they give you. Multiplicity is a very important tool to use when analyzing NMR spectra, and really helps you put together pieces of your molecule. Now, as mentioned previously, this provides information about the number of neighboring hydrogen, which is a nebulous term that we're going to dive into in this video. Briefly, there are three types of neighbors that are characterized by their distance, which is the number of bonds apart. Now, what does that mean? It means that if we have HA, for example, right, and it's connected to some molecule, and maybe it has some distance to a different signal like HB, these hydrogens are close enough that they might interact with each other in some way, and we can observe that in the NMR spectra. One thing I want to be clear on, though, is that in situations where we have HA on both sides of the molecule, these are not going to act as neighbors to each other, as they are the same signal. So to be clear, only different signals, or chemically inequivalent signals, are able to, quote-unquote, split the signal or act as neighbors, which we'll talk about in more detail. The first type of neighbor is the 3J neighbor, okay? So we're going to define these J values here. Now, this is a very simplified version of what this really means, and when you go into the J values in higher level organic chemistry, you'll see that there's a lot of rich and complicated information about them. For now, I'm going to break them into three different types. The 3J neighbor are neighbors that are characterized by being 3 bonds apart, and another name for this relationship is vicinal, or vicinal neighbors. Now, these are the most common. When we talk about simple splitting, we really only deal with 3J neighbors. And honestly, they represent over 95% of the neighbors that you're going to run into when you're first learning about NMR in an introductory OChem course. Here we can see an example where we have HA and HB connected to 2 carbons. We can see, obviously this isn't the complete molecule structure, just the idea that HA is 1 bond connected to this carbon, 2 bonds for carbon-carbon, and a 3rd bond connecting to HB, meaning that we have a 3-bond distance between these 2 different hydrogens, and they would be neighbors to each other. An example of a molecule that has this kind of neighboring is shown to the right here. Let's quickly discuss this. So let me color code some hydrogens in, and we can talk about the different kinds of neighbors. So here, this red signal, right, these hydrogens that are on this methyl group on the left side of the molecule, we can see that all of them individually, so when we look at neighbors, we view the signal as kind of one big piece. We can see that they're all 1 bond away from this carbon, a 2nd bond, carbon-carbon, and there's a 3rd bond that leads to these other hydrogens. We can call them signal B, right? We can see how A and B then are neighbors to each other. Now A would have 2 neighbors, since there are 2 neighbors on B, right? But A would never be a neighbor to itself. In the same sense, B is also going to have A as a neighbor, except it's going to have 3 neighbors on that side, because A represents 3 hydrogens. Importantly, we also have signals here, and we can see that B and C are also going to be neighbors. We'll discuss in more detail what that looks like, and how 3J neighbors really show up on the NMR spectrum, but for now, that's the introduction to 3J. Now, the more common and less common, more difficult types of neighbors that you may run into are 2J neighbors. So 2J neighbors are defined by being 2 bonds apart. So they're kind of close. They're neighbors that are living in your upstairs attic instead of your next door. And we call these geminal, or geminal coupling. They're quite rare, and they exist in some scenarios we've already talked about, which is when 2 distinct hydrogens share a carbon. Remember that this can happen when rotation is restricted. For example, in this case of this alkene, and in this case of this ring. Both are rotationally locked systems. HA and HB here are different, as HA is cis to this oxygen and HB is trans to it. We can see that HA and HB are both 3 bonds away from HC. That is, that HC is a 3J neighbor to both HA and HB. However, HA and HB are also going to be neighbors to each other. They're not identical anymore. Their distance is 2 bonds apart. The same is true on this ring. Recall on this side that HA is on the same side of the ring as the OH, and it won't be able to rotate, so it will be at a different chemical shift than HB. We'll see two different signals. Even though they're on the same carbon, they're 2 bonds away, they can be neighbors to each other. The last kind, there it is 4J neighbors. Now these are pretty rare, but they're 4 bonds apart. We sometimes call this long-range coupling or W coupling. And in this course, or at this level, they're very typical on benzene. So the basic idea is that when you have a pi bond or some sort of pi system, and you can draw a W between 2 hydrogens, you'll notice that there's 1, 2, 3, 4 bonds connecting them. They'll be able to be neighbors as well. While there are situations that this occurs outside of the context of benzene, this is really the situation you should be aware of when initially learning the material. Great. So in total, we have 3 different types of neighbors, 3J being the most common, 2J and 4J being rarer, but they're really defined by their distances. So what does this actually lead to? Let's quickly talk about Pascal's triangle and how that helps us with splitting. So Pascal's triangle, if I zoom in here, is a quick little mathematical puzzle that, I don't know if that was initially, Pascal didn't discover this for NMR, but we ended up using it, and you'll see why later. The idea is that you take a 1 at the top, then you have 2 terms, 1 on both sides, and you keep adding 1 on the sides. However, once you have a third number, you can add these numbers up to get the number in between. The same pattern continues, and you can continue this pattern in perpetuity to get some pretty weird patterns. This triangle actually is very relevant when we talk about the shapes of our peaks, as we'll discuss. So simple splitting occurs when all of the signal's neighbors are the same type. Okay? What that means is they're all the same distance. For now, we'll deal with 3J as that's going to be the most common case. Let's look at HA. In this molecule here, we're going to have 2 different neighbors on this carbon and 6 different neighbors on these carbons here. So these are going to be one signal, and these are going to be another. But from the perspective of HA, we could say that it has 1, 2, 3, 4, 5, 6, 7, 8 neighbors. Or we could even say that, if we wanted to, that they are 3J apart. So we have 8 neighbors that are all the same distance. Recall that these, while they are different signals, right, these hydrogens are not going to be equivalent to these ones. They are still 3J, or 3 bonds away from HA, making them the same type of neighbor. Same here with HB. We can see that there are 3 hydrogens on this methyl group to the left, 2 to the right, meaning that HB has 5 neighbors. Right? They're all, once again, 3 bonds away, so 5 neighbors of the same type. Remember that since HB is the same as HB, these are not going to be neighbors to each other. We wouldn't include that as a type of 2J neighbor. Excellent. So now that we've kind of looked at this idea of the neighbors being the same distance or the same type, let's take a look at Pascal's triangle. So interestingly, as we're going to have here, this is the number of peaks of the signal. I'll draw the shape of the signal. We'll give it a name, and we'll figure out the type of information we get. So one peak of one height, we can start with the lowest number of peaks that's possible, right? 1 peak. If you have an NMR signal with 0 peaks, you just simply don't have an NMR signal. The shape is going to look something like this, just 1 peak, and we call this a singlet, sometimes just denoted as lowercase s. Now what this tells us is that we have 0 neighbors nearby. It doesn't tell us the distance, but it just says we have no neighbors, there's no splitting going on. Okay, that makes sense. We'll touch on this idea again, but keep in mind that 0 is the lowest possible number of neighbors you can have, and 1 is the lowest possible number of peaks. If I jump that peak number up to 2, we get an extra peak, right? So these are both going to be the same height. Notice, like in Pascal's triangle, they're the same 1-to-1 height. We call this shape a doublet. And what this indicates to us is that we have 1 neighbor. That is, 1 hydrogen took that signal and kind of split it into 2. So far, this seems pretty easy, but now we're going to kick it up a notch. with the third peak. Now, many students might expect, reasonably so, that we would get a shape like this. But this is not correct. When it comes to simple splitting, what we actually observe is peak height distributions of 1 to 2 to 1. Notice once again that it is symmetric by the center, increasing on this side and decreasing on this side. Right? Kind of like a triangle. The peak heights are 1 to 2 to 1. And you'll notice that that is what we get when we apply Pascal's triangle. Interesting. This gets a name called a triplet. Oh, it's actually a D, my bad. D, this is your triplet. And that indicates that you have two neighbors. Last but not least, and again, we can go into much higher. I'm only going to show you these four, but the logic continues as you go following Pascal's triangle. We get 4 peaks. Remember, this is not a quartet. The peak heights must follow Pascal's triangle of 1 to 3 to 3 to 1. This is a quartet and represents 3 neighbors. Right? So that's how Pascal's triangle helps us understand the name of the shape and what they look like. But at the end of the day, the key idea here is that the shape of the signal gives you some information about the number of neighbors that that hydrogen signal has. Right? Let's do a quick example, just looking at this. So here we have 2 hydrogens. We'll start with this one. We'll call this signal A. And looking over here, 3 bonds away, we have HB. HA has no neighbors on this side, as there's no hydrogens connected. That means that from HA's perspective, the only neighbor it has is one neighbor, which is HB. Given that it's one neighbor, we would expect to see a doublet. Right, looking back at the table, one neighbor shows up as a doublet. Okay, so we got a doublet there. HB is going to be an interesting one. So here we have 6 different equivalent hydrogens. Call them all HC. Now HC, it's going to only have one neighbor as well, right? It's too far away from HA. It can only have its 3J coupling with HB, so it's also going to show up as a doublet. But HB is stuck in the middle. It has 2 neighbors on its right side, 6 neighbors on its left, for a total of 8 neighbors. Now, I didn't include that on the chart, but keep in mind this pattern. If you take the number of neighbors and add 1, right, you get the number of peaks. Or I guess we could do that. So 8 neighbors would be expected to have 9 peaks. Now, the name of this, and they're worth memorizing, is the nonet. Okay, and remember that you're going to see basically 1, 2, 3, 4, 5, 6, 7, 8, 9 peaks with that centrosymmetric pattern. Okay, just an example of how you can look at a structure and get those, understand what those multiplicities might look like. Now, let's talk about a couple common mistakes to avoid. The first is incorrectly converting peaks to neighbors, or neighbors to peaks. Right? You might be asked to do both on a typical test. What some instructors will suggest is to use this n+1 rule or n-1 rule. The idea being that we can understand, oh, a triplet must always be 2 neighbors, so it's always -1. So take the number of neighbors, right? Or take the number of peaks, multiplicity that is, and subtract 1 to get the number of neighbors. That works great unless you're asked to get the signal. Then you have to add 1. And in my opinion, this isn't a great way to go about this problem because you have to memorize the correct equation to use, and if n-1 and n+1 are way too similar, you'll easily make mistakes. My advice is to use the smallest as a prototype. Right? Remember that a singlet is the lowest number of peaks you can have. Right? 1 peak. And that 0 neighbors is the lowest possible number of neighbors. Right? To me, what this does is it kind of sets the relationship. And as long as you remember that, which to me is pretty straightforward, right? You can't have less than 0 neighbors, can't have less than 1 peak. Once you know the singlet and the 0 neighbor relationship, and you draw that out if you forget, you'll be able to reverse engineer those rules, right? Oh, a singlet is 1 peak representing 0 neighbors, so from going to peaks to neighbors, I must subtract 1. Vice versa, I would add 1, right? Remember that prototype and you'll have a lot more success and avoid that really catastrophic error of, if you put 4 neighbors here, you're never going to get your NMR spectrum correct. Okay. And the second one, as I previously mentioned, is incorrectly identifying what are called complex multiplets as simple multiplets. The key difference is that the simple multiplet follows Pascal's triangle. And those signals are always going to be what I call centrosymmetric. Right? Or centrosymmetric triangles, in a sense. Right? Where we have kind of peaks increasing to the middle and then decreasing beyond that point. In situations like this, where we have more than 1 or 2 peaks, right? A doublet would look similar, but 4 peaks, that would actually be a complex multiplet, which we'll be investigating in the next video. Remember that, by the way, if your professor in your institution isn't covering complex multiplicity, feel free to skip the next video and jump right to video 1.7. But if your curriculum is covering it, I'll absolutely do my due diligence, and I'll see you in video 1.6 to understand what's going on with these weird complex multiplets that don't seem to obey that Pascal's triangle rule. I'll see you there.